an introduction who Darren is. Darren is the technical lead of the family-run business Waterware. The company specialises in medium-sized plumbing, bathroomware, heating and cooling solutions. Darren is responsible for the system design, commissioning and troubleshooting support, and is backed up by Rob Scholtens in the position of the National Specifications Manager. The family company specialises in providing solutions with a design and after-sales support package. Waterware supports solutions for radiant heating and cooling systems and high-capacity hot water systems. The company promote renewable appliances, developing heat pump systems offset by solar PV arrays for carbon neutral and low running cost heating, cooling and hot water generation. The company are a CIBSE affiliate member. Over to you, Darren.
Thank you, Les. Hello, I'm Darren from Waterware, Technical Director. I've been at the company, started in 1992, so yeah, part of the furniture there now. Over that time, we've had a lot of experience with mostly boilers. So we've done a lot of radiant heating systems, starting way back in the day with diesel boilers and gas boilers, and then transitioning to gas condensing boilers. And then over the sort of the last 10 years, what's been entering the market is air-to-water heat pumps. And so during that transition, we've gathered a lot of experience with using these types of appliances, and we're starting to now really, with these new refrigerants and new technologies, we're moving more and more into radiant cooling solutions, which is a relatively new technology, and more into high capacity hot water systems with high temperature heat pumps. So today I'll just go through just the general lay of the land about what sort of technologies are available and some of the contrasting features and benefits of them. It won't really be related to any brand in particular, but at the end we'll go through a few, just a couple of live examples which we have up and running and commissioned and seen them working. So just to start, I'll just go through and let's bring that one. Next one up. How do I go to the next slide? That one. I'll just go through actually what a heat pump is. Depending on what background you're coming from, heat pump technology can be a little bit bewildering about how super high efficiency appliances like this work. And like when you look on the face of it, you know, you can have appliances which are running at 400% efficient, and you think, well, how is that actually possible in terms of efficiency? So when you're coming from a boiler background, typically you'll supply it, let's say 1 kilowatt worth of natural gas or diesel, and the boiler will combust that, turning that into 999 watts of heat if it was 99% efficient or at some sort of rate of efficiency. So, and when you have an air-to-water heat pump, that's not what happens. So when you supply an air-to-water heat pump 1 kilowatt of electricity, it's used to run a process, and what the process is it takes the source, whether that's air or water or groundwater, and it runs it through a refrigerant process. The power is used to power a compressor, and inside the refrigerant circuit, it manipulates the latent point of the refrigerant, the gas in the circuit, by compressing it, which obviously increases the pressure, and then expanding it, which decreases the pressure. And through this cycle, it allows you to do a magical thing where you can harvest energy from the source which you're using. So most common, which we deal with, is air-to-water heat pumps. So you'll have outside air on one side of the circuit, and then you'll have a plate heat exchanger with water on the other side of the circuit. And the real magic of this is you can do it at a greater than 1-to-1 efficiency. So when you see efficiency stated for air-to-water heat pumps, or in fact any type of heat pump, it's stated as a COP, a coefficient of performance. And this describes how much energy you can harvest from your source relative to the input. So if you give 1 kilowatt of electricity to your appliance and it's got a COP of 4-to-1, it'll give you 4 kilowatts of hot water back. And so this is the type of efficiencies which are typical depending on the application. And that's why this this technology is really being used in this more and more in the market, is because of these very high efficiencies which you can have, and also if you're supplying it with green produced electricity, then you get very good bang for your buck in terms of carbon footprint and those sorts of things. So just to summarize, with an air-to-water heat pump, it runs at what we call a COP, coefficient of performance, and it's always stated as a ratio. Depending on the application, it'll be 3:1, 4:1, 5:1, is not uncommon. And what that means is the input is the 1 kilowatt and then the output is the other number, so 4 kilowatts, for instance. So one thing which, something which is changing continuously in this space is the refrigerants. So I'll just give you a general overview of the common refrigerants available in the market today. And the refrigerants have an environmental score which we call GWP, global warming potential. And it's basically the amount of damage which gets done to the environment if you let off a kilo of gas. And they give it a score. And the gold standard currently is CO2, which has a GWP of 1, which means it's basically inert. You can let the CO2 off and it doesn't do any greenhouse damage, so no warming effect with it. The older gases which are fast being transitioned out, most common is R14A, and that has a GWP of 2100 units. So it gives you an idea of sort of the lay of the land, which these GWP scores are stacked up in. So some of the other, in hot water production, you see reasonably some units which use R134A, and that's about 1500 units. R32, not so common in hot water production. I'll explain why when we go through a little bit further. That is a GWP of 675, and R290, which is the technology which we've been using most in this space, has a GWP of 3. So it's very close to CO2 in terms of its GWP. Now, there has been just recently a recalculation of these GWP scores, and R290 has been rescored at 0.2, so it is in fact below what CO2 is now, and R32 has been rescored, and I believe it's at 775. Going over the 700 threshold creates problems in terms of, well, not problems, but challenges in terms of meeting the world's reduction goals when it comes to GWP. And so there may be some changes in the market which are going to come if this reallocation of GWP is ratified. So it's just something to be aware of, that they are working on this these technologies all the time, or these scores. And over time, these older gases are being phased out, and you can see on the timeline there, starting in 2015 going out to 2030, there is a schedule of reduction in GWP, which has been agreed to as part of the Paris Climate Accord, I think it was. One of the other things just to be aware of is one of the ways, rather than just make gases illegal, what they do is they start to tax them heavily. So as an example, when I started with refrigeration appliances maybe 15 years ago with R14A, a jug of R14A gas was about $400, and now the same jug is about $3,000. So what happens is they attach a carbon tax to this refrigerant, and they basically make it uneconomic to keep older appliances going just by making the refrigerant more and more expensive. So that's something to be aware of, as well as just when you're thinking about the life cycle of these appliances. These older based refrigerants are going to naturally become more and more expensive to run as the cost of getting this refrigerant just goes up and up. Okay, so when most people, when the retail, the masses think about heat pumps, almost always they're thinking about air-to-air heat pumps. So you have an indoor unit, and then you have, an outdoor unit, and then you have an indoor unit which blows hot or cold air. And these type of heat pumps, they're very simple to install. They're very, very cost effective. But some of the limitations with them is you're bringing refrigerant inside the building envelope. It's mostly only used for space heating applications, and it's mostly R32. So one of the issues with R32 is if you're trying to use it for an air to water application, both R14A and R32 have a, due to the pressure in the refrigerant circuit, which they're rated to operate in, they have a limitation of how hot they can get water. So typically on a good day, the maximum water temperature you can get from an R32 or an R14A appliance is 62 degrees. So it makes domestic hot water application, especially commercially, it means that to deliver a system using this type of refrigerant, typically you'll have electric boosting because you can't reliably sterilize the tank for Legionnaires. So, and also with these refrigerants, as you approach the maximum temperature, the efficiency of the appliance goes down quite a lot. So if you're always operating right on the envelope of what's possible with an appliance, your COP will not be very good. And so that affects the efficiency and the performance of the appliance. You really want to have a bit of tolerance between the maximum temperature possible and the maximum temperature which you're setting to give you a bit of headroom. So, and just to clarify about bringing the refrigerant inside the building envelope, the reason why this is becoming more and more important is the newer refrigerants, what we call the natural refrigerants like R290, that is actually propane. So it is flammable gas. It's classed A2, flammable gas. And so with these types of refrigerants, which are very, very good in terms of GWP, are not very flexible when it comes to actually piping it through the building. So it's unclear about where this particular market's going to go, these very cheap split systems, because if R32 becomes uneconomic because of the GWP score, it's unsure about what refrigerant they'll actually move to if they're looking at bringing the refrigerant inside the building envelope. So I know Mitsubishi have quite a clever system called an HVRF, a hybrid VRF, which has an outdoor unit and then what they call a hydro box, or BC box they call it, and then that converts it to water. So while you have air-based technology inside the building, it's more fan coils. And so they circulate water through the building rather than refrigerant, and that may be a way forward for this sort of technology. So typically this is only used like commercial, but you might find this pushing more into high-end residential and maybe going heavy commercial as well. Okay, so another very common technology in the market at the moment when it comes to air to water heat pumps, if you want to produce domestic hot water, a very good technology or one which has got some significant advantage over the R14A and over the R32 is CO2. So a CO2 heat pump, we call it a single pass air to water heat pump. I'll explain why that is in a minute. It has the gold standard in terms of GWP, has a GWP of 1. It has very, very high temperature output. So you can reliably get up to 80 degrees on the flow, which obviously opens up the domestic hot water production where you want to keep your tank at 65 degrees for sterilizing. So that's very possible with a CO2 heat pump. In the right application, a CO2 heat pump is very, very good. I'll just explain about some of the limitations and what single pass means in a minute. In terms of capital cost, they're reasonably expensive, but not ridiculously so. So in terms of on a cost per kilowatt basis, they're a bit more expensive than an R32 or even an R290 appliance, but they still create some value. Now, single pass. So what does it mean to be a single pass? What it means is across the heat exchanger inside the outdoor unit, it's looking for a very big delta T. So to get a good COP out of these appliances, typically they target a 50-degree difference. So if you've got 20-degree water coming from your hot water system, it rises it up by 50-degree rise and then returns it to the hot water system at 70 degrees. That has some challenges. Just to give some context around this, ties back into how you size these units, and I'll just give an example of coming from gas technology. on a cost per kilowatt basis, gas is very, very cheap. So when you're designing a production system and you're thinking about, okay, this is my target, which I'm trying to achieve in terms of production, there's a number of ways you can do that. And with gas systems, typically it's almost what we call semi-instantaneous, where you have very high recovery and a very small amount of storage. And the reason for that is, and it typically would be like a bank of infinities, for instance, and then some buffering between the building and the infinities. And the reason for this is, in terms of cost per kilowatt, these appliances are very, very cheap. So on a cost per kilowatt basis, gas is very cheap relative to the cost of storage tanks. And so to hit your production values, it makes sense to go heavy on recovery and light on storage. You're still hitting the same production value, but you're doing it almost in a semi-instantaneous way. So the duty cycle of your appliances do most of the heavy lifting during draw-off. And then after draw-off's finished and you've got some recovery to do to bring your tanks back up to 65 degrees, the amount of time or amount of energy which is added into those tanks during that time is limited, and then you have maintenance, so basically recovering ring main losses. So it's helpful to think about your duty cycle in those three chunks. So you've got production under draw-off, you've got your draw-off energy, you've got your recovery energy, which is after the draw-off is finished, but you still need to recover your tanks up to 65, and then you have your maintenance, which is your ring main losses. Okay, so when we come to size systems with heat pump technology, it's a little bit different because your heat pumps are very, very expensive in terms of cost per kilowatt, and proportionally it makes the cost of storage much cheaper. And also when it comes to installing these appliances, it's much, much cheaper to put in a big gas pipe than it is to put in a big electrical infrastructure. So typically what we find with these jobs is you're always pushing for amps. You're always kind of jammed up in the maximum number of amps you've got available. And so when it comes to sizing these systems, you start with the same production value, but it makes sense to do this in a more storage and recovery method. So you have a much higher level of storage, and then you recover it over the 2 to 3 hours between your peak periods. So for unit tidal accommodation, for instance, it's not uncommon where you'll have a peak period in the morning where you shower 60–70% of the people in the building. Then during the day, you have very low draw off. And then in the evening, you might have another half peak period where you shower the remainder of the people. So some people shower in the morning, some people shower in the evening, and that's kind of typically how the duty cycle on these systems work. Now, with a heat pump driven system, it makes a lot of sense to supply the majority of your water from a stored buffer and then recover it over the next 2 to 3 hours after that peak period is finished. And so that changes the mix and the design of the system. Rather than having this semi-instantaneous system where you've got huge amount of recovery power and a small amount of storage, typically that gets flipped around. So you have a large amount of storage with a smaller amount of recovery. Total production over the peak period will be the same, but you're doing it in a different way. Okay, so we've just got that for context. Now, when we look at CO2 and single pass, these appliances are very, very efficient during draw-off. Why is that? It's because you have an unlimited supply of 20-degree water coming from the street and filling the system, and your heat pump can operate on that very cold water, and it can heat it up in a single pass. So it can go from 20 degrees up to 70 degrees and then pop it into the top of your buffer. But it doesn't make sense to do all of your energy in that way because the size of the heat pump required to keep up with your instantaneous load is way too big. And so typically you still have a large amount of buffer with a small amount of heat pump. And so now when you have a look at the duty cycle, you'll still have a significant amount of energy which you're putting into the system during recovery. So you'll serve your hot water for the building. Then over the next 2 to 3 hours, you'll be recovering those storages and you need to get them back up to 65 degrees to sterilize them. During that time, as the delta T across the appliance gets compressed, then the efficiency of a CO2 appliance goes down significantly. So because you no longer have an unlimited supply of 20-degree water available to be putting through your heat pump. Now you're operating on your storage temperature, and your storage temperature obviously goes up as you get closer to the 65-degree target in your cylinders. So what you tend to see with a CO2 based system is they have this, what do they call it, a shift load system. So rather than have, let's say for instance, you've got 3 hot water cylinder storages, rather than have 3 in parallel, which would be most common for a gas-fired system. And the reason for that is, if let's say you've got 3 1,000 litre tanks, if you have them connected together in parallel on the potable side, it means that if you've got 3 tanks, they'll all be at 65 degrees. You'll have 3,000 litres of 65-degree water ready to deliver to the building. A shift load system is different, where you have, rather than the tanks being in parallel, they're in series. So you feed from the first tank into the second tank, from the second tank into the third tank, and from the third tank to the building. And the reason they do that is because when you start drawing water off, the first tank goes almost completely cold, and then you have a second tank which is warm, and then you have the last tank which is still hot, supplying the building. And so that allows you 1,000 litres of reasonably cold water, which you can still run through your heat pump, get a reasonably good COP. But as that system now starts to recover and get back to 65 degrees, then you're compressing the delta T across the appliance. You'll still be delivering at 70 degrees, but you won't be getting a 50-degree rise anymore, because now you've got 30, 40, 50-degree water going back to your heat pump, and the efficiency is going down and down and down. So much so that typically in these systems, you'll see that a CO2 heat pump will be partnered with electric backups. So part of that is because of this compressing of the COP across the appliance and the stress it creates on the compressor when it's not operating in single pass anymore. And part of it is because they don't do very well in partial load. So if you're just trying to recover ring main losses, a CO2 heat pump doesn't do that very well. So typically they'll do that with an electric backup. Okay, so the limitation of that is you can now no longer create a clean model about what the efficiency of the heat pump will be in this application, because it is totally tied to the duty cycle of the building. So if the building is under light load and you don't have unlimited supply of cold water to run through the appliance, and 70% of your energy is in recovering the tanks rather than during draw off, the COP of the system would be quite different. Firstly, because you're compressing the delta T across the appliance, and secondly, because your electric boost is going to be working to keep that final tank at 65 degrees. And then once your recovery phase finishes and now you're into maintenance phase where you've just got ring main losses, that's all done by electric boost. So it's very hard to create a model about what the actual efficiency, what the energy use, what the COP of the system will be, because it's not directly tied to what the COP of the appliance will be in its optimal condition. Okay, so if we compare that to an R290 system, an R290 is much more like an R410A or an R32. It's what we call multi-pass. So a multi-pass appliance is not looking for a 50-degree difference. It's looking for a 5 or 10-degree difference. So it works much more like a boiler, where you can have 50-degree water returning to the heat pump. It'll heat it up by 5 degrees, put it back into the cylinder. Now you'll have 55-degree returning. It'll heat it up to 60. Now you'll have 60 returning. They'll heat it up to 70. And the COP across the appliance is very consistent. So it doesn't, the duty cycle of your hot water system doesn't affect the COP greatly. The only things that really affect the COP is what's my primary flow and what's my outdoor air temperature. So to create a model for the performance of the system is now much cleaner and much more consistent. And the heat pump also does very well under partial load. So you do not need any electric element in the system for operation, only for redundancy if you want that. So recovering ring main losses, things like that, an R290 system does absolutely no problem. So the advantages of your R290 in this multi-pass becomes kind of apparent, where you can design your system much more like you would a gas boiler, indirect gas boiler based system. You can have your hot water storages in parallel rather than in series. And so if you've got 3,000 litres of water stored, all 3,000 litres of water when you've finished your recovery cycle will be at 65 degrees. So now you can deliver that all in one hit into your building in a much more consistent way. So the advantages of your R290, it's got low GWP. So currently score of 3, that might be revised down fairly soon. high temperature output, so it'll reliably put out 75-degree water all day long. So you can have 70 on the return, 75 on the flow. You get very consistent, good COPs. So real world operation, we're getting between 3.5 would be typical. So 1 kilowatt in, 3.5 kilowatts of hot water out. The hydraulics are very simple. It's much more consistent to how you would design a mechanical boiler system, where you've got flow and return, and on the potable side, your cylinders are plumbed up in parallel. It's also suitable for many applications. So it's not just hot water applications. What you can do, any sort of space heating application, whether it's radiant systems, fan coils, anything like that, because it's very comfortable operating on a 5 or 10 degree difference, then you can use them multi-use in all sorts of applications. Capital cost is fairly good. It's a bit cheaper than CO2. It's a bit more expensive than R32, but it kind of sits in that middle ground. But one of the limitations, or one of the things to be aware of with these appliances, is it's propane. So it is a flammable refrigerant. It is an A2 scheduled gas. So you do have to be a little bit careful about where you put the appliance. But the risk is reasonably limited. So to give you some context around that, a 20 kilowatt air-to-water heat pump has 1.7 kilos worth of gas in it. So compare that to a 9 kilo barbecue bottle or a 90 kilo twin pack, which a lot of houses around New Zealand have sitting on the wall. The risk is reasonably limited, but it does limit where you can put the appliance. Has to be outside, has to be in an area with free ventilation. Can't put them right next to a gully trap. There's a meter exclusion zone. But beyond that, it's reasonably easy to find a location for these appliances. Okay, so this is an example of what the units look like. They're monoblock, and so what monoblock means is that refrigerant never leaves the appliance. We're only circulating water backwards and forwards, and they have basic system components built in. So primary circulation, safety valve, those components are actually inside the jacket. So hydraulically, when you come to connect to them, it's very simple. On the primary side, you don't need to do reverse return because each unit has its own pump and controls its own speed across the exchanger to optimize for that 5 degree difference. And again, it's comfortable, multi-pass, 5 or 10 degree difference across the appliances is perfect. And typically we run them in cascades. The reason for that is it gives you very wide modulation range and it gives you redundancy. So if we have a system which requires 80 kilowatts worth of recovery, typically we do that with 4 appliances. And that will give you a modulation range from one appliance on 30% output, which is its lowest modulation. They've got full inverter technology in them, is about a 6 kilowatt output. So you can continuously modulate your array from 6 kilowatts to 80 kilowatts, depending on demand. And so that does very, very well under both recovering your system where you need high power and then maintaining your system when you've just got ring main losses or very small hot water loads to serve. The system's very, very comfortable in doing that. Reasonably quiet. So at 1 meter, it's 47 dBA. So they're reasonably easy to cite in terms of noise. We've done a lot of work in the aged care space for rest homes, and they're very sensitive about noise. It seems old people are happiest when they're complaining, and so they're very mindful of creating any noise issues with these appliances, and these are really quiet. So especially when they're on low modulation, you have to struggle to see whether they're actually going or not. So one of the other things with R290 appliances, they have a really, really wide operating range in terms of ambient air temperature. So they'll operate right down to -25. So the COP is terrible, but they'll still operate at -25. So the operating range is really good for these appliances. So they don't run out of legs once you go below 0 degrees. The performance of them, the performance curve is relatively flat. Okay, so some of the other components which we put into these systems hydraulically, these are indirect appliances. So this is mechanical water which we're putting through the heat pump. We're not running potable water directly through. Typically with CO2, they are direct, so they have potable water going through them. One of the limitations of that, and the reason why they do that is because they're always trying to optimize the delta T. They're trying to get that single passed operation going as efficiently as possible. So if you can send cold water from the street directly to the appliance, then that's their happy place. because we're operating on multipass and we're quite happy with warm water going back to them, we typically, well, these appliances are only for indirect application. So hydraulically, the way we set them up is we have an array of appliances. If we're doing hot water production, for instance, we always have a minimum of 2. So we've always got some redundancy built in. And hydraulically, it connects onto a buffer tank, which hydraulically separates the appliances from the load. I'll show you a drawing in a second. And what that allows you to do is to run the cascade in a very optimal way. So if only one heat pump needs to run, then there's no water going through heat pumps 2, 3, 4. You've just got heat pump number 1 running, and that populates the buffer with 65, 70 degree water. And then we pump out of that buffer to a plate heat exchanger, and then your storage tanks then go through the plate heat exchanger. So we have a break on the other side of the buffer where we use a very large plate heat exchanger with a very small temperature difference across it. So typically we've only got a 2 or 3 degree difference between the primary flow from the buffer and the secondary return going back to the storages. So if we've got 67 degree water in the buffer, we'll have 65 degree water going to the storage tanks. So we oversize the plate heat exchanger to allow us to operate in that way. More and more, we're starting to use pump stations. So a pump station is just a very easy and convenient and tidy way. It's an insulated clam. It gives you multifunctions in one group. So you've got a pump with isolators, check valve, flow and return, temperature gauges, and there's a range of headers where you can join multiple pump stations together. And I'll show some applications where we do that. And we also have what we call a mixing station. So it's exactly the same, but it's got a 3-way valve built into it. And you can control the 3-way valve using a 0 to 10 volt output. And so if you've got a variable temperature application, so going to an air handler, for instance, then we can use pump stations going to pool heat exchangers, and then a mixing station going to the air handling unit. So I've got an example where we did this exactly. Okay, so water quality across a plate heat exchanger is always fairly important. So we do magnetic straining on the primary side. So again, the water that goes through the appliance is reasonably limited. So you might have 300 or 400 litres of water in the system, your buffer, your primary mains, your plate heat exchanger, and then to your appliances. And then we use a magnetic filter to strain that water, and we use dosing for chemicals into that water as well. One of the other advantages of having an indirect system, which I should have mentioned, is we've got double wall separation between the refrigerant and the potable water. So the appliance operates on the mechanical water, and then we have another heat exchanger which separates the mechanical water from the potable water. Where if you've got a CO2 heat pump which is operating on the direct water, and if you have a leak in that exchanger, you have the refrigerant and oil going directly into the potable water. So it's not double wall separation. Okay, so air to water heat pumps, one of the advantages in multipass anyway is these flexible duties. So from one appliance, you can do a multi-use system where you've got low temperature radiant heating, like underfloor heating, for instance, high temperature radiant heating through radiators. We can operate 65 degree flow and send them to the radiators, no problem. We can also do radiant cooling, which is a new technology which we've brought to the market. It's got automatic 2-point management to avoid condensation on the radiant surfaces. It means that you can have an underfloor heating system which works in cooling mode, and we can deliver about 25 to 30 watts of cooling to the space. So, and in terms of comfort, it's a very big increase in comfort over a solely air-based system, and it's much more efficient than doing an air-based system. So we've done a few repowers where we've had underfloor heating systems driven from gas boilers, and we've replaced the gas boiler with an array of heat pumps and the right control pack, and then you can have that existing floor system which now does heating and cooling. So so that's available as well. We also do fan coils, and then of course domestic hot water production, which I've alluded to quite a bit through this presentation, and pool heating as well. Okay, so just a word on system efficiency. Just because you can doesn't mean you should. The efficiency of the appliance is very much tied to 2 things: what the outside ambient temperature is and what primary flow the heat pump is producing. So you can see the highlighted row there to contrast this. So at a 7-degree outdoor, going from a 75-degree flow temperature with a COP of 2.15, exact same appliance, exact same conditions, but with a 35-degree flow temperature, almost double the efficiency, so 4.1. So it gives you an idea of just how important it is to think about what you're going to use your appliance for, and if you've got any scope to lower the water temperature. So sometimes you might come into a job and they've got a gas boiler system which they need to replace, and they're thinking about doing it with air to water heat pumps. And let's say it's a classic that we see a lot is an underfloor heating application with domestic hot water. It's in your interest, it's in the system's interest to actually split that into two systems. So you can have one system which is running at low temperature all the time and another system which is running at high temperature all the time. If you combine that into one system and you run high temperature all the time and then you mix that water down for the low temperature application, the efficiency you'll get out of the system is about a half of what it could be. So you should always be asking your questions when you're doing these specifications. What's the lowest primary water temperature I can use to achieve the duty which I need to achieve? And so if we're going into a system with a pool heating application, for instance, and we're replacing a gas boiler, and they've been running the gas boiler at 65 degrees and the plate heat exchanger is sized to do that, it makes a lot of sense to increase the size of that heat exchanger and lower the primary flow temperature down to 45. The additional efficiency you gain out of the appliance more than offsets the cost of increasing the size of the heat exchanger. So this is true in terms of heat exchangers for pool heating applications, air handler units, fan coils. Sometimes it can be well worth the trouble to increase the size of the coils to be able to lower the water temperature in the system. Okay, so here's an example of a system which we did for an aged care application. And it was a pool heating application where they had an indoor pool and they had a pool, a spa pool, and an air handler. And the key metric for them was to reduce carbon, and all of it was run on gas. And so we replaced the gas appliances with an array of 4 heat pumps. So we've got 80 kilowatt input, and you can see it's hydraulically separated. So the heat pumps connect to the buffer, and then the buffer connects to the pump stations and the mixing station. And so I think this system we ran at a 45-degree flow temperature. There was a gas burner which was in the existing air handler unit, which they removed and replaced with a water coil, and then we connected that onto the system using a mixing station. And the reason why we used a mixing station was the air handler wanted to be able to vary the water temperature depending on the load. So if it's a very low load, they might send 20-degree, 25-degree water to the coil of the air handler, and if it's heavy load, they'll send 45-degree. And so with a 0 to 10 volt input, on the mixing station, you can connect that along with your pump station. So we populate the buffer with 45-degree water. We pump that water directly out to the pool heat exchanger and to the spa heat exchanger. And then on that same manifold, we can have a mixing station where we can do variable water temperature. So yeah, that's the design in that system. We have another one which is similar. So this is a hot water system where we've got 60 kilowatts of recovery, and I believe it was 2,000 litres of storage. And you can see hydraulically how similar it is. So the air to water heat pumps connect onto the buffer, and then we pump out of the buffer. We've just got a single pump station on the system, and you can see where the plate heat exchanger is leaving the pump station. So that's the break between the mechanical and the potable water. And then in the storage tanks, all we have is a recovery pump, which moves the water from the bottom of the cylinder through the plate heat exchanger and then delivers it back into the top of the tank. So the tanks themselves are hydraulically separated. You have a separate cold in and hot out, and then we've got dedicated recovery ports on the side, so we can circulate the water through the plate heat exchanger independent of draw off. That gives you the most consistent delivery temperature out of these tanks, where you can arrange it that way. Sometimes we've got a bank of infinities. I see they use the bottom connection of the tank for the recovery to the infinities. and I'm not a particular fan of that, because sometimes you'll have water entering that port, and other times under recovery you'll have water exiting that port, and it's a bit odd to have water traveling in both directions through those ports. So wherever possible, I like to have dedicated recovery ports so we can completely hydraulically separate. So very simple hydraulically. The pump comes on, sucks water out of the bottom of the tank, drives it through the plate heat exchanger, and then drops it back in again. We do individual pumping on the cylinders, so you've got redundancy rather than just having one pump. And it also means that you don't have to do a reverse return circuit to balance the flow in any of these. The heat pumps have got their own circulating pump, so you don't need reverse return on the primary. And then the hot water cylinders have their own circulating pump, so you don't need reverse return on the secondary either. So very, very clean in terms of system design. Sorry about that. And yeah, very clean in terms of system design. Very simple hydraulic arrangement. So on the cylinders, you've just got a manifold cold in, manifold hot out. The cylinders are in parallel, so you're delivering all of the water at the same time through both tanks. No electrical element required. This particular system, we're flowing 70-degree primary flow, and then we're at 65-degree target temperature in the tank. And again, it's ring main compatible. This particular array will go from 6 kilowatts to 60 kilowatts on the production side. So I'm very comfortable recovering ring main losses and things. You get a bit of stored inertia in your buffer tank where you've got 100 litres of water in there. And so, yeah, under maintenance, under ring main losses, the system just ticks along very comfortably. Just a quick word about buffer tank sizes. So coming from older appliances which had non-modulating compressors, we used to see these systems had really, really big buffers on the to connect multiple appliances together. With these new appliances which modulate so well, the requirement for having big buffer now is nowhere near as high. All we really have, the only real reason that we need the buffer there is to provide some energy for a defrost cycle. So if one of the appliances has to go into defrost, it uses the hot water in the buffer to actually melt the ice. And with the cascade controller that we use, that is actually managed across the array. So if you've got one heat pump which is currently going through a defrost, it'll hold the other two heat pumps in production to keep the system running. And then once that first heat pump has finished its defrost cycle, if one of the other two require it, then that one will start. So the system will only allow defrost on one of the appliances at a time. So all that sort of logic's all kind of built in on the cascade controller. Okay, so that is the end of the presentation. Hopefully that was clear and gave you some context around what's kind of happening in this space, in this renewable space, specifically around hot water production, but also replacement of gas appliances for multi-use like pool heating, air handling, fan coils, that sort of thing. I'm not sure if there's a method for questions. Or if there's any questions, if someone wants to pipe up anything which is unclear.
Thanks, Darren. There is a Q&A box for questions if anyone has any.
Yeah, I've just got a quick one, Darren. It was on that system efficiency where you had that little chart up. It was the R290 COP, and yes. As I can see, it goes from 35 through to 75. So it was, as it was going up 35, 45, it was getting less and less efficient. But then between 60 and 65, the 65 picked up efficiency. It went from 2.56 to 2.72. I don't know if those figures are probably around the wrong way on that. I think that's what's happened.
Yes, they might be. I hadn't actually seen that. I'll have to dig into that, have a look, because when you look at 10 degree, 15 degree and 20 degree, that doesn't happen.
Yeah.
Oh,
yeah,
no,
so
it does it 20 degrees as well. Yeah, I'll have to just have a look at that.
Yeah. But yeah, that's the only question I've got.
Okay.
Does anyone else want to ask anything?
No, nothing from me. I thoroughly enjoyed that.
Yeah,
thanks.
That was my second time of listening to it, and I learned a little bit more. And I'm sure if I listen to it a third or fourth time, I'm going to keep learning. So yeah, excellent. That was really, really good, Darren. And yeah, this will go on to our CIBSE website. So we might as well wrap it up now. And thanks once again to our presenter. And wish you all a good day. Okay,
All right,
cheers, everyone.
Thanks
Thank you,
very
Tim.
much. That
Bye-bye.
was really good.
Thank you.
Thank you.
Bye-bye. Thank you.
Thank you.